Hello class! The next type of force we'll cover is friction. Friction is caused at a microscopic scale, and it all depends on the type of surface. Every surface has a specific coefficient of friction. If an object is moving across a friction surface, it will have a coefficient of kinetic friction. Remember, kinetic means motion. If a force is applied to an object resting on the friction surface, it will have a coefficient of static friction. As the force increases, so does the frictional force until it reaches a breaking point, where the object starts to move across the friction surface. Below is a table of different coefficient of frictions for static and kinetic. The coefficient of static friction is at its maximum value right before the breaking point of where the object starts to move. Once the object moves, notice that the coefficient of kinetic friction and even friction will drop in value. Here is a graph displaying the frictional force applied to an object starting at rest. At first, the object does not move, and the frictional force keeps increasing as more force is applied on the object. This region is considered static friction. Then finally, there's a breaking point and the object starts to move with some constant frictional force applied. This region where the object is moving is known as kinetic friction. Let's go ahead and do our first example. Our 10-kilogram mystery box rests on a horizontal table. The coefficient of static friction is μs, which equals 0.4, and the coefficient of kinetic friction is μk, which equals 0.3. Determine the force of friction, F sub Fr, acting on the box if the horizontal applied force, Fa, is exerted on it of a magnitude of part A, 10 newtons, and then part B, 40 newtons. First step is to use the definition of friction for static friction. Notice that the equal sign we are finding at the maximum value of friction right before the object begins to move. But before we can plug and chug, we need to find the value of normal force. To do so, we need to take some of the forces in the y direction, set it equal to 0 because this box is not floating in the air nor sinking in the ground. Next, write down all the forces applied in the y direction, which is positive normal force and negative weight. Then solve for the normal force, which equals mg. Plug and chug to get 98 newtons for the normal force. Finally, we can use our friction equation to solve for the maximum force right before the breaking point of where the object starts to move, and we get 39 newtons. So the box will not move if the force is equal to or less than 39 newtons. Once the force applied to the box is greater than 39 newtons, the box will begin to move on the frictional surface. In our first problem, letter A, for the force applied is only 10 newtons, which is way below 39. Thus, the frictional force will only equal 10 newtons applied in the opposite direction to have some of the forces in the x direction equal 0. Now, for part B, the force is greater than 39 just by 1 newton. So we get the plug and chug with using the coefficient of kinetic friction instead of static. And now we get a frictional force of 29 newtons, while the object is sliding across the surface. Now the sum of the forces in the x direction is greater than 0 and has the remaining resultant force pointing in the positive x direction. Here's another example. A 10-kilogram box is pulled along the horizontal surface by a force Fp of 40 newtons applied at a 30-degree angle above the horizontal. Assume the coefficient of kinetic friction of 0.3, and we want to calculate the acceleration. Now, in most problems, our object will be moving with friction pointing in the opposite direction of motion. First thing is to draw a free body diagram displaying all the force vectors applied on the object. Then, write some of the forces in the x and y directions separately. In this example, the object is only accelerating in the x direction. Next, we want to draw the component vectors for any vectors not along the coordinate system. In this case, we only have one at an angle. Now we can write all of our forces in the x direction, then all of our forces in the y direction. Fpx is a component of our angle vector and can be rewritten as Fp cosine 30, and the same with Fpy, except it's sine 30. We can also make a substitution for the definition of kinetic friction, which is mu Fn. Now I went ahead and rearranged the equation in the y direction to solve for the normal force, because I know we'll need it in the x direction for when we solve for acceleration. Plug and chug for the normal force, and we get 78 newtons. Then rearrange the other equation to solve for acceleration. Plug and chug, and we get 1.1 meters per second squared. Alright, next example. Now we have two boxes connected by a cord running over a pulley. The coefficient of kinetic friction between box A and the table is 0.2. Find the acceleration of the system. First step is to draw a free body diagram. Notice that tension is equal but in opposite direction, and that friction points in the opposite direction of motion. Next, apply the trick with the pulleys. That is, to straighten out the pulley and redraw the forces appropriately. Please press pause if you need to understand this diagram. Now we have our vectors drawn. We can write the sum of the forces in the x and y direction separately. With the way I've drawn the diagram, the system is moving in the x direction. Keep in mind that this is relative to what the original diagram displays. For our whole system, we write down all the forces in the x and y direction separately. Since we're analyzing the whole system, all the masses in the system must be included on the right-hand side of the equation for the x direction, which is ma plus mb. And look at that! Tension cancels out. And I know we need to solve for the normal force in the y direction for a later substitution. Our equation reduces down in the x direction and the y direction. We can plug and chug to solve for the normal force, which is 49 newtons. Next, solve for the acceleration of the whole system. Make the substitution in for friction, which is the coefficient of kinetic friction times the normal force. Plug and chug to get an acceleration of 1.4 meters per second squared for the whole system moving. Now, our last type of scenario will come across our objects on an incline. The main trick for solving problems with an incline is to redraw your coordinate system along the inclined plane, as seen by the x and y black lines drawn on the figure to the right. Now let's say we have a skier that has begun to descend the 30-degree slope. If the coefficient of kinetic friction is 0.1, what is her acceleration? Our first step is already done by drawing in all the force vectors on your object along the coordinate system drawn at an angle. Now look at the force vectors carefully. Are there any vectors at an angle with respect to your coordinate system? If so, which one? Yes, you got it. It's weight, mg, that is at an angle with respect to your coordinate system. Next step, with any vector at an angle with our coordinate system, is to draw its components along the x coordinate system and the y, as seen by the orange and blue vectors. Now, one geometric rule that you may need to pause to think about is that the incline of the ramp, which is 30 degrees, equals the same angle as drawn in red on the figure. This will be helpful to know later on with our equations. Again, we write the sum of the forces in the x and y direction separately, though keep in mind with our coordinate system, which is now angled. Next, write down all the force vectors along the x and y direction separately. Again, please note how these vectors line up with our angled coordinate system. We can rewrite our weight in the x as mg sine 30, which is referenced by the blue force component on the figure, which is opposite of the red angle of 30 degrees. We can also make the same substitution for weight in the y direction, which is the orange vector as mg cosine 30. The last substitution we need to make is friction, which equals mu Fn. Notice in the y direction I have already solved for the normal force, as it's a common substitution in the x direction. However, notice that we can't solve for the value of normal force because we don't know the mass of the skier. However, we can make a substitution n for the x direction. So let's do that. Do you see what cancels out? Roger that. It's mass. Now our equation reduces down to the variable we want to solve for, acceleration. I went ahead and factor out g. Now we can plug and chug to get about 4 meters per second squared for the acceleration of the skier.